Okay, everybody, it's fantastic to see a really packed kick off the term. So it's my absolute pleasure to welcome you all back after the summer break to our new Colloquium series, where the organisers Alex and B-Way have put all the hard work and put together a really impressive schedule for the term. And today, we're really excited to kick off the programme by welcoming Dr. Tim Brandt, who's visiting us from the Space Telescope Science Institute. You're no stranger, though, to Princeton, and having completed your PhD here, undertaking a census of giant exoplanets, before you then came to the Institute as a NASA Sagan Fellow. So, yeah, welcome back.
Thank you.
Subsequently, you moved to UC Santa Barbara as an assistant professor, before returning to the East Coast, where he continues to pursue an ambitious research agenda. In particular, Tim develops and uses a diverse suite of observational techniques in order to detect and characterize massive planets and brown dwarfs, which we will be hearing more about today. So without further ado, let's welcome Tim to the floor.
Thanks very much. It's wonderful to see everyone. It's been, I think, 8 years since I've been here, and it's good to be back here to see everyone. So I want to start by highlighting a subset of my collaborators. I couldn't fit everybody on here. Red is my current grad student, Shiran, and I'll highlight a little bit of her work later. Blue are all of my former students, some of whom have left into industry, some of whom are current grad students. So you'll see not all of their work, but you'll see smatterings of some of their work throughout the talk. And I'll try to credit everything that I didn't make myself. So if there's a figure without attribution, then hopefully I'm not taking credit for what somebody else did. Hopefully I remembered all of those. I'll start, since this is really an observationally driven field, with a little bit of the history of exoplanets, going up to 2020 and going up to 2020 for a reason, because things have really changed in the last few years in a good way. For a long time, the only planets we knew about were a subset of the ones in their own solar system. Mercury is off below the bottom of this plot, so that's why you're not seeing it. Mars also is a little bit low to be on this plot. The first new planet to be added to this plot was found by just looking around the sky for things that moved. And that was in 1781, and there it is, Uranus. So that was the first discovery from blind search. The second discovery was completely different. That was from an understanding of celestial mechanics and the fact that Uranus didn't quite follow the orbit that it should if we had a complete understanding of the solar system. So you could predict a perturbing body, and it was subsequently found Neptune. And that's going to have echoes in some of the things I'll discuss later in this talk. And then things got difficult because we found all of the major planets around our solar system, at least unless Planet 9 is still out there, waiting to see, I suppose. But finding planets around other stars has been very difficult. They've long been hypothesized, but it took a long, long time for our observational techniques to catch up. And it wasn't until the 90s that we really started to find them. And in this movie, the first ones are going to be actually pulsar timing planets. The first planets that you might think of as being around a sun-like star were discovered in 1995. That was 51 Pegasi b that earned the Nobel Prize, and Gliese 229b that will also make another encore appearance later in this talk. After that, things really started to heat up. More and more planets came. They were found by different techniques, and those are listed in the right. So radial velocity was the most productive way of finding planets early on, where you're measuring the reflex motion of the host star along the line of sight. Imaging was an early one, where you're actually directly seeing light from the companion. That's also going to be a significant focus of this talk. And that is much more sensitive to bigger things farther from their stars, where it's easier to separate the light. Transits have filled in things really, really well, especially since Kepler and TESS. And I know that Joshua and Gus Hipparcos here have done a huge work on transits. And then finally, you start to see a smattering of points labeled astrometry here. That's also something that will come up later in this talk. And so that's kind of where we were a few years ago. And I'll pick up from there. So there are a number of different ways of finding planets, and they give you different information about the planet. So a transit, play that again, is when the planet passes in front of the star, plot some of the light. And that gives you a measurement of the planet's period if you observe it happening repeatedly. And it tells you how big the planet is compared to the star, how much of the light it's blocking. So it'll give you a radius, basically. If you have radial velocities, you're measuring a Doppler shift of the star along the line of sight. You're really measuring a velocity. And that's going to give you a handle on the period if you follow up the full orbit and on the mass of the companion. But you don't know the orientation. So you can have the same signal from an edge-on planet or a more oblique planet, and you can tune the mass to get the same radial velocity signal. So it's going to give you the mass, but subject to some uncertain inclination. It's not going to tell you how big it is or what it's physically like. If you put radial velocity and transits together, then you have a size and a mass, but somehow it doesn't give the same visceral reaction as looking at them and seeing what they're actually like. So that's the goal, right? We want to take these planets, see not just how big and massive they are, we care about that, but what these worlds are actually like. That's where the field would ultimately like to go. On Earth, for our own solar system, it's not so bad. We look in the night sky, but on other stars, it's pretty hard because planets are faint. If I put the sun here, a black body to crudely approximate the sun, and then put Jupiter the way it is today, then the space between those two curves is about 9 orders of magnitude, which is the brightness ratio of a stadium to a single firefly. And that is well beyond what any of our telescopes can do today. There is a telescope called the Nancy Grace Roman telescope that aims to do something close to this, and it'll launch next year. I'll say a few more words about that, not specifically about the chronograph, at lunch. That's my day job these days. What people realized, Adam was one of the people who did this about 30 years ago, 5 years ago. It doesn't have to be this bad. On Earth, right? If we're trying to do this contrast during the day, it's a little unpleasant, although still the light's pretty spread out, so you can do it. And I think, Bob, you've taken pictures like this during the day. But we can just wait and use the Earth as a giant light blocking tool, and then everything's great, right? So on Earth, the Earth itself allows us to see the solar system planets very easily by just waiting till nightfall. But we can't do that trick on another star. We would have to physically have some kind of an implement that we make to block the starlight unless we get vanishingly lucky with some kind of occultation. So what Adam realized was that if you have Jupiter not as we see it today, but as it was when it was young and still radiating its heat from formation, then you're not necessarily 9 orders of magnitude off. Maybe you're more like 5. And this is now within the realm of what is possible with ground-based telescopes as of 15 years ago, 20 years ago. And so that's how this field really got going. And that was kind of my introduction to this field when I was here at Princeton. So if we look at a star, then to the extent that we can correct the atmosphere, what we see is basically a diffraction pattern from the telescope optics. And if you look at that, the core is blown out because of saturation, so don't worry about that. But you see not just a point, you see all kinds of stuff from this diffraction pattern. And you want to know, is it just a star or is there something else there? So what we would do on the ground as we take advantage of the fact that we are on a rotating Earth and our perspective changes as the night goes on. So anything from the optics is going to change orientation relative to the sky, kind of like this. And so now you can see very easily where the companion is and which of those spots is really astrophysical. This goes by the name angular differential imaging. You can dig a little deeper and you can find things, call it 10 to the 6 times fainter than the star. And so that's kind of the rough number that we had earlier. And so I spent my PhD, many other people spent their PhDs doing this kind of thing, looking for planets, and we found a few. There was great excitement, especially about a couple of the early discoveries. This was maybe the splashiest. The system is called HR8799. All these planets have phone number names. But you see 4 planets around this one star. This was a big deal and got everybody really, really excited. And then we didn't find so much else. So we got some discoveries, we got really excited, we built lots of new instruments, and then there was kind of a trickle of things that came out. A new generation of instruments would find a couple of new planets, right? And even then, when you see a planet like this, you're seeing how luminous it is, how much light you're getting. And the IAU definition of a planet is based on mass, at least the draft definition. So people would argue over what the mass is. We're not measuring it. We're measuring the light from the planet. If you want to know the mass, you need to have some model with a bunch of other information, like how long it's been cooling. You don't know how old the star is. We can make guesses, we can have constraints. But the amount of ink spilled over arguments about how old the star is kind of absurd. We don't know how old these stars are in many cases. Some we know pretty well. And so we don't know how massive the companions are. We don't know how to physically interpret some of even the small set of objects that we find. So that was the state of the field 15 years ago. Some successes, some disappointments. So we had a ways to go. And in this talk, I'll tell you about a huge amount of progress that's been made using 2 of these different advances. One is individual field spectrographs, and the other, even more recently, is astrometry. I'm not going to talk about the bigger telescopes and space missions. This is, well, it's the notional 30-meter telescope. We'll see if that actually happens. The European telescope is under construction. That one on the right, though, that one's looking pretty good. The Roman Space Telescope is in thermal vacuum testing right now. So it's cold, under vacuum right now, and undergoing final testing before launch. So the integral field spectrograph that I know best is one that was actually built right here in Princeton, over at the Mechanical and Aerospace Engineering building. It's called CARIS, and it was built by Tyler Groff back when he was here as a postdoc. And I wrote the data pipeline for it. So it's a lenslet-based spectrograph. I want to give you a tiny bit of intuition for how it works, and then try to show you the extra power that it gives you to find and characterize these kinds of planets. If you have an ordinary camera, you put a detector in an image plane, and you get a picture. It's a single color. Maybe you put a filter in front of your camera, so you get a picture in one color. Maybe you then put another filter and take a picture of another color. This is a typical way you would conduct astronomical observations. For an integral field spectrograph like this, you don't put a detector at that focal plane, you put a lenslet array. Each lenslet takes that area of the field, brings that light down to a little itty bitty point, so that in this intermediate stage, most of what you have is empty space. You have a detector that's mostly empty with a very sparse array of points, and then you can use a prism or some dispersing element to spread out the light of each of those points. And then you get a whole bunch of itty bitty spectra. So this is what a diffraction pattern might actually look like as seen by the lenslets. The lenslets then focus it down to a bunch of points, and so now your detector is being used very inefficiently. But then you use a prism to spread each of those out. And so what you're seeing in that little inset are all kinds of little spectrum. Each of those lines is the spectrum of a single lenslet. You see a couple of little.
What is the resolution of the spectrum?
In this case, this covers the JHK band, wavelength ranges from about 1.1 to 2.4 microns at the resolution of about 20. So very, very low resolution by spectroscopic standards. And those dark spots you see are the regions between bands where the Earth's atmosphere is relatively low. CARIS also has higher resolution modes where you take one of those bands, JH or K, spread it out a little bit more, and so you get less wavelength coverage, but higher resolutions of maybe 80. So these are low resolution instruments because we don't have that many photons from the star. You can do other things where you do take them to higher resolution and you take advantage of other effects, but those are other instruments that I will not discuss today. If you reconstruct the data cube, what the image looked like at each wavelength, you get something like this. This is a single 20-second image compared to a long sequence of images that you saw before. And so take a look at it again and see if you can spot the companion. So diffraction scales with wavelength. That's why the whole thing appears to grow. You can see that wavelength figure on the bottom right. Look for the one thing that isn't moving out from the center. And there it is, okay? So that's a brown dwarf. And now we can find the brown dwarf without having to take a full sequence. This is just in 20 seconds. And what's more, we can get a spectrum of it because we have the light at each individual wavelength. And so these instruments are hugely powerful, made us significantly more sensitive, and we got another trickle of detections. So Keras is one of these telescope or one of these instruments. There's also GPI and Sphere. GPI is on Gemini and Sphere is on the European DLT. And each one found their 1 or 2 planets or something. So again, a trickle, but not the flood we were perhaps hoping for. There were claims before GPI was built that maybe we would be able to discover and characterize hundreds of these things. And that didn't happen. We do get spectra, yes.
That's just an occurrence rate issue, or were there other reasons that people were overly optimistic?
People were optimistic about performance, but by and large, it's an occurrence rate issue. If you take occurrence rates at small separations and you take a power law and that power law is flat or increasing and you extrapolate out, then that's a lot more optimistic than something that falls on. So that's the primary issue. And so once we find these things, oh, and I should also say, please feel free to interrupt with questions. Once we find these things, we do see signatures of molecules. We do actually learn about their atmospheres. So there's something about spectroscopy that gives us something that radial velocities, transits just can't do unless you're talking about the very outer layers of the atmosphere of transit spectroscopy. So there's a little bit of an asterisk where transits can do a little bit of this, but really for atmospheric characterization, I think the long-term path forward is going to be. Okay, but it's hard. And the history of this field is one of big dreams and somewhat disappointing results, where we have wonderful results, but we haven't quite realized what we were hoping for. And we've always done our best, but always kind of hoped that things would get better in the future. To put rough numbers on it, we spent a couple $100 million on instruments specifically to target these things, and we've invested a huge amount of telescope time, and it's gotten us, before, and as of a couple of years ago, something like 20 image planets. And mass was always an annoying problem where we could estimate the mass using models, but we didn't have any first principles measurements, and so we would have arguments over how massive these things really are and how to interpret them physically. Because if you have a 5 Jupiter mass thing, you have a different physical interpretation than if you have a 30 Jupiter mass thing.
Attention, follow up with spectroscopy on the radial velocities on the star.
You can, but if you have something on a 100-year orbit, that's pretty tough. And some of these stars are not friendly to radial velocities. So if you have a 5 Jupiter mass thing on a 100-year orbit, then to get a full radial velocity characterization, you have to wait 100 years.
It's gonna lower down.
Right, but now you're talking just how significantly can you measure a trend? And for a lot of these, it's just not been doable, especially because for directly imaged planets, you want things that are young and hot. And if you have a young star, it's going to be faster rotating, more magnetically active. And that means that the photosphere is going to be messier, and it's going to mean that your RVs are going to be messier. So your typical radial velocity precision on a young star just isn't good enough. So the set of stars for which we have first principles, dynamical masses, and imaging was 0 until around 5 years, a little more than 5 years ago. And that's something that, again, I'll come to later in the talk, because it's not 0 anymore. Yes.
But those planets are quite far away from the star, right?
Yes. The
So
imaging
if you
ones.
compare to the distant planet from Kepler, does the comparison better?
Well, Kepler wouldn't find planets as far as the imaging ones at all, because Kepler is going to need to find multiple transits. So they're really disjoint populations of planets.
Exactly,
You could,
so that's not really a fair comparison.
oh, and no, it's totally not a fair comparison in terms of dollar per planet, because I would argue that these planets are more valuable than these ones. Absolutely. Of course. The question is, how can we make these numbers look better? Yes.
So when you say you expected to find many more and you find fewer, based on what would you expected to find many more and what does it tell us?
So.
You take all the observational selection effects.
So a lot of the early planets were discovered with radial velocities. There are some selection effects that go into what you choose to observe, what you're sensitive to, but people did their best with the demographics analysis of radial velocities. And they fit some models of planet occurrence. And then some other people said, well, if I take that model and I push it farther and farther out, hey, there should be a lot of things out there. And well, it goes down. So there weren't as many as we hoped for, but it was extrapolating demographics that were inferred from radial velocity observations. Okay, so the rest of my talk, I will pivot into a different field that's taken off in the last few years and that has the power to really address a lot of these issues, and that is astrometry. This is a picture of the Gaia spacecraft, which is at L2 and just ceased observations, I think a few months ago. So Gaia took data for about 10 years, measuring the positions of stars incredibly precisely from about 2014 to just recently. And that's what I'll talk about now. So astrometry, I don't know how much experience people here have with the field. It just means measurements of a star's position. So if you have a star and it's merrily zooming along through space on an inertial path, then it won't have a purely straight line path as seen from the Earth because the Earth moves. So the motion of the Earth introduces something called parallactic motion on the star due to our changing position across the year. That's the middle path. Then you have the inertial path, of course, of the star. You put them together and you get a sky path like you would see on the right. So an astrometric mission like Hipparcos or Gaia is going to fit paths like the one on the right. And each one depends on 5 parameters. Position, that's 2 numbers. A proper motion, which is what we call a space velocity. That's another 2. And a parallax, which is the amplitude of that parallactic motion. It's a linear fit, and that's what Gaia does many times. If you have a companion around the star, then this does not fully describe the sky path. You have that sky path plus orbital motion. So that's what we're looking for. Can you distinguish this extra bit from that inertial 5-parameter sky path? Now, this paper was written, I believe, at Princeton about 2014. So it was written a little more than 10 years ago. And this one claims for plausible assumptions on planet occurrences, a few thousand planets. And there have not been a few thousand Gaia planets. There have been a couple detected so far. So I want to tell you a little bit about why that is, what the sensitivity and selection effects of astrometry are, and what we can do in the meantime in addition to what's coming. Because I think there are good reasons why we haven't realized this yet. I don't think it's a fundamental problem with the observations at all. So why? The most basic reason is because Gaia has finished observations, but it hasn't released all the data yet. And the measurement precision depends on exactly what it is you're trying to measure and how long you watch something. If you're trying to measure just the position, then if you observe it for longer, you improve your measurement as the square root of time, the square root of the number of measurements. If you have a slope, it's different. Because if you observe it for twice as long, you have twice as much data, so that's the square root of time. But you also have twice as much signal. And so that's a factor of 2. So put them together, you have a precision that scales as t to the 3/2. So the precisions on velocities will increase pretty steeply with the baseline of the mission. Parallaxes won't improve that much for Gaia, proper motions will. And if you get to higher order nonlinear terms like accelerations, it's even steeper, the dependence. So for acceleration, if you observe for twice as long, you have 4 times the handle on that quadratic term. And so your precision for accelerations goes like t to the 5. So if you care about something like this, then it makes sense that, well, Gaia has a ways to go yet. That's why we haven't seen all these thousands of planets today. We can combine these scalings with Kepler's third law to get an idea of what Gaia's sensitivity will look like and how it's going to change with time. For short orbital periods, you just care about the amplitude of the signal, scales with the separation of the planet and the mass of the planet. It's just how big the orbit of the star is going to be. And I can substitute in for a separation using Kepler's third law to get a t to the 2/3 power, and that is the red line. At longer periods, I'm basically just measuring an acceleration, which Newton tells me is m/r². I again sub in Kepler's third law, and I get that purple curve. They cross basically at the mission lifetime. Because at the mission lifetime, you cover the full orbit. That's where you really change from measuring this motion to measuring an acceleration. So that blue is a Monte Carlo using actual orbits and realistic simulations. And those other 2 curves are using that fiducial scaling. So the fiducial scalings really work well. As Gaia continues observing, that red curve will move up as t to the 1/2, but the purple curve will move up a lot faster, and the peak sensitivity will continue to move outward. So as Gaia continues to observe, we will do a lot better at the long periods, and our peak sensitivity will gradually move to longer and longer periods. Gaia has taken 10 years of data, and a big part of the justification for the extended mission was exactly this. It wasn't for measuring better parallaxes, it was because of the very steep dependence of sensitivity on mission baseline for things like orbits and accelerations. And so a 10-year Gaia baseline is going to really push that out. So that's what we're waiting for, is the larger data releases, along with the work to make sure that the systematics are well understood and calibrated as much as we can. Okay. Right now, we have Gaia DR3, the 3rd data release. We're patiently waiting for DR4, which is going to be in 1.5 years, something like that. But there is something we can do. This isn't the whole story, because there was another instrument called Hipparcos, also launched by the Europeans, that observed the positions of stars about 30 years ago, actually 35 years ago, in the late 80s and early 90s. And so that anchors these measurements pretty far into the past. And so that's going to lead me to a brief pop quiz. I'm not going to call on anyone. Gaia, if you go to the catalog, you look it up online, it's going to give you a bunch of information about the star. Among those will be a position and a proper motion, a velocity in the plane of the sky. If you look up Hipparcos data, you're going to get the same thing, position and the velocity. So how many proper motions are drawn on this figure? Drawn's 2, but implicit is 1 more, because I have 2 positions and I know when the missions were observing. So I have 3 proper motions here. One of them is actually integral proper motion, but I have 3 proper motions, 3 things with units of velocity. And that one, the green one, has 25 years in the denominator. And getting to divide by 25 years means that an uncertainty from Hipparcos doesn't sting quite so much. Hipparcos can be less precise and still be powerful. And if I think of this as an acceleration, something else amazing happens. Gaia and Hipparcos are anchoring things to some fixed celestial reference frame, or as fixed as they can get it. So this is really motion in an inertial reference frame. And if I just go to first semester physics, then gravity in an inertial reference frame will exert a tug, gm/r². And so that's what I'm measuring, is the tangential component of gm/r² as a star is tugged by a companion. There are some things you have to be aware of, a little careful of. Gaia and Hipparcos are not measuring instantaneous velocities the way radial velocity does. That really is measuring a velocity via Dopplership. Here we're measuring positions, and we're fitting a line to positions. Remember from that sky path earlier on, it's a fit to that linear model. And so if you have significant curvature during those observations, then what you see is not going to be the instantaneous position and proper motion at any point in time. It's going to be some sort of average. As the period gets longer and longer, and it becomes closer and closer to an instantaneous position and proper motion. But this is something you have to be a little bit careful of. So when I use things like accelerations and put very simple equations, in practice, we're going to need to resort to orbit fitting, but the equations and the simpler arguments will provide the intuition. So I'll stick as close to those as I can for the intuition. If you want to do the orbit fitting, then there are tools to do that. And that's what you would do to actually analyze data. Okay, this is much more sensitive to nearby stars. And you need the orbital periods to be long enough that that blurring on the last slide isn't too bad. If you close an entire orbit during Hipparcos or Gaia, well, then that kind of average position and proper motion starts to lose all resemblance to the orbit. And it depends on exactly what was observed when. It becomes very tricky to back out. As you get to longer periods, that becomes less and less of an issue. Also, astrometry is measuring angles on the sky. It's not measuring physical separations. So if you want that angle on the sky to be as sensitive as possible to a physical separation, you want it to correspond to a smaller physical separation. So you want your star to be closer. This is much more sensitive to nearby stars. Yes.
So Hipparcos never released their per epoch astrometry. They did. So
Yes.
you have that in principle, right? So, and-
It's not trustworthy, but yes.
Yeah.
So there are two reductions. I don't want to get into this too much. There are two reductions of the Hipparcos data, actually three. The European Space Agency combined the first two and released the catalog in 1997. And Floor van Leeuwen did his whole reanalysis and released a new catalog in 2007. That new catalog is based on fitting the spacecraft motion in a way that uses a huge number of free parameters. So a large fraction of the information for the bright stars was actually used to reconstruct the spacecraft position. There's very little left to get the positions of the bright stars. And so it's not really possible, in my opinion, to use those data for orbit fitting. This is something that I'm working on now, is trying to understand exactly what happened. But they did release the individual epochs. I don't think there's much you can do with them.
A question about orbital fitting. Do these fits account for radial motion? Are these in like three-dimensional? Are these made in three-dimensional space or
Yeah.
in two-dimensional angle? Because
It's
overlay
using the
is
standard Keplerian orbital elements and you just fit them to whatever parameters you have. So you might fit only the 2D projection, but under the hood, yeah, it's going to be doing a three-dimensional model.
do Hipparcos and Gaia have like this level of precise measurement of distance to notice like the distance change?
Oh, do they have that precision? No, the change in parallax, a change in distance to us is tiny, much too small to be measurable for any of these systems.
But it would have to be accounted for in proper orbital fitting, no?
If you really wanted to do everything exactly correctly, yes, but these are higher order effects that are not relevant at these precisions. Yes.
Thank you.
Okay. So what if we don't just have astrometry? What if we also have radial velocities? Well, radial velocities, those measure the motion of a star. And if I correct for the motion of the Earth, again, this is an inertial reference frame. So a radial velocity trend or an acceleration is just the orthogonal component of the transverse acceleration measured by astrometry. If I also have the projected separation of the plane of the sky, then I have three equations and three unknowns. I can just solve that by algebra. And so all my problems of masses are solved if I have these three measurements and I have them reasonably precise. So great, right? There's a catch. And the catch is that you have to trust the data to be able to pull this off. You have to take Hipparcos and Gaia and be able to put them together to merge the two data sets. They don't have cross-calibrated uncertainties. They're not quite in the same reference frame. There are all kinds of devils in the details. And if you really want to interpret them statistically, you have to confront this. And so that's what I've done over the last few years in 2018 and 2021, is to try to take these two data sets and merge them in a way so that they can be used to fit orbits. And the basic tool I'm going to use for this is to assume that most of the stars are going in a straight line. And for most of the stars, do these differences in proper motion divided by the standard error, does that look like a unit Gaussian? This is called a z-score. And the answer is no, it doesn't. So that black dashed line is a unit Gaussian. And those colorful lines are the difference between the Hipparcos and the long-term proper motions for stars of different brightnesses. The brighter the star, the worse the agreement. This is a symptom of the fact that Hipparcos errors are severely underestimated for bright stars, because so much of the information for bright stars was used to reconstruct the spacecraft attitude itself, and that wasn't accounted for. So we need to inflate the uncertainties, and it turns out we actually average all the Hipparcos reductions together to get the best answer. Gaia, same sort of thing. Again, the uncertainties are underestimated. This is to be expected. So this isn't a problem per se. It's only a problem if you're taking the catalog uncertainties that you download from the internet and assuming that that's the full story. It's not. And if you read the Gaia papers carefully, they never make a claim that it is. Okay, so these kinds of underestimated uncertainties are expected by the Gaia. So we need to fix this. And I'm not going to go into any of the details of how this was done, but the final step, I'll summarize the final step. Because the final step turned out to be pretty tricky for the most recent Gaia data release. In order to see whether the stars show that expected behavior for the unit Gaussian, I want to pick stars that really aren't accelerating. And that's tricky, finding a set of standard stars. So in order to do that, I turn to radial velocity to find a sample of stars that were not accelerating this way, and then assume that if I threw out all the stars that were accelerating this way, I would have a sample that, well, not perfectly clean, was at least pretty clean of stars that were accelerating the orthogonal way. And if I did that, I took the RV standards, and if I inflate the Gaia formal uncertainties by about 35% or so, then I take these distributions, which are just a bit wider than the unit Gaussian, and make them statistically indistinguishable. So there's other evidence that the Gaia uncertainties for these bright stars are underestimated by something like this. And this is just another piece of evidence. So now, to the extent that that does look like a unit Gaussian, my data do pass the tests so that I can use them to actually fit orbits, measure masses. Yes?
Is it only a multiplicative fraction, or is there also an additive term?
I found no evidence for an additive term in Gaia. I found no evidence for a multiplicative term in Hipparcos. Hipparcos is best treated with an additive term, Gaia with a multiplicative one. Why? There are lots of gremlins in the Hipparcos data. I'm still digging into it. I don't. The final precisions that we get are astonishing. So those units up there are microarc seconds per year squared. A microarc second is something like 10 to the minus 10 radians, 10 to the minus 11 radians. So this would be a human, the thickness of a human hair is seen way down this, maybe in New York City. This is an astonishingly small angle in the sky. And it's possible now with a combination of Hipparcos and Gaia. All right, the final ingredient to this is to fit orbits. So there's an example. Here's the catalog that I constructed for this purpose. You do have to be a little bit careful. I'm not going to go into those caveats too much here, but these are suitable for orbit fitting. I wrote a code to do this with student Yiteng and with my other students called Orvara. And there are some other codes that are useful too. Octofitter, I want to advertise that a little bit. it's using Hamiltonian Monte Carlo and written in Julia. So if either of those things strike your fancy, I think this will be one to watch going forward. This has some cool features in it. And we are actually modeling the orbit through those individual measurements. We're trying to do a pretty thorough job of everything. And there's a lot you can do once you add this last ingredient. So for radial velocities, we measure just m sin I. We measure the mass subject to an uncertain inclination. If you add in the astrometry of the star, then you can constrain that. You break that degeneracy. And so this is work that was just accepted by my student Han, showing a population of radial velocity detected companions in mass and semi-major axis, where now it's actually mass on the vertical axis. It's not m sin I. And you can see these two populations. It's not the first time this has been seen, but it's one of the cleaner demonstrations of it, I think, where you see a cluster of points in the top right. These are stellar companions. And you see another cluster of points below, things that presumably formed like planets. And it looks like the colors are a little bit different too. The color is coding the eccentricity. So stars are a bit more eccentric. Planets, presumably they formed in disks, they're a bit less eccentric. Again, not the first time people have looked at this. I know Lauren Biddle here has worked on that, but a nice demonstration. Even starker, if you frame things in terms of a mass ratio, which is perhaps a little bit more physically motivated. A very clean separation between the higher mass stars and lower mass planets. Moving beyond just RV surveys, here's an example of a Princeton adjacent brown dwarf discovery, LISA 758b, that was discovered with the high child instrument used on the SEED survey, which was a big Princeton collaboration back when I was a student. So it was discovered in 2009. And in 2018, Brendan Bowler wrote this big paper constraining its mass and orbit. So he fit radial velocities, you see those on the left, and he fit the motion around the star on the right. It's a pretty long period. And so the orbital constraints that he was able to get, they were okay, but not great. You can see that the period is fairly uncertain, almost a factor of 2. The mass is also pretty uncertain. It could be anywhere from about 35 up to over 100 Jupiter masses. So not useful for pinning down the models of what this is actually like. A year later, less than a year later, I fit basically the exact same data set, but I added one more ingredient. And that was absolute astrometry from Hipparcos and Gaia. Not even the most current one, but the data release 2 that was available at the time. And watch what happens to that mass constraint on the top right. The x-axis changed. And so you go from a mass that could be anywhere from 35 to 100 Jupiters, to suddenly you have a few percent dynamical mass just from Newton's laws. So that's what's possible now with this one additional ingredient. The period is still about 100 years. So we haven't measured the orbit, but it doesn't matter. We've measured enough to get a really precise mass. It's even starker if we go to another object. This is just one more visualization of the difference it made in the dynamical mass from that to that. And again, the x-axis changed. So this goes from 0 to 100, this goes from 0 to 60. And now we can start to pin down these kinds of models of brown dwarf cooling. The first secure T-dwarf that was ever imaged around a sun-like star was discovered in 94, 95. That was on that first movie, LISA 229b. I add this one more ingredient to the data that have already been supplied. It has about a 200-year orbital period. And in 2020, I got a mass of about 70 Jupiters. This was a lot higher than we expected. The discovery paper thought it was maybe 40. So this was deeply puzzling. My student, Mirek, no relation, despite the shared last name, he updated this analysis with Gaia data release 3, which was a significant improvement in precision. And despite the fact that the orbital period is 200 years, he derived a 1% mass. And if you're thinking, wait, a 1% mass, does that mean that you're measuring the acceleration with 1% precision? Yes, it does. In the Hipparcos Gaia catalog, this acceleration is significant at I think about 115 sigma. So just astonishing, okay? The kinds of things we can do for well-behaved nearby stars. And this just didn't make any sense from a substellar evolution perspective. You'll notice that these curves, these dotted lines, show you how bright, how massive you can possibly be, even if you give yourself 10 billion years to cool, and this thing the star does not look 10 billion years old, and still be as faint as what we see. So Adam's models are the only ones that are tolerable at all, and that's before he's added the most recent sources of opacity, which would push that to the left, okay? So it just doesn't make sense. Our idea for how to harmonize these things was, what if its mass isn't actually 70 Jupiters? What if it's more like 50 and the rest is in some very, very faint companion? What if it has a hidden friend that's a reservoir of some of that mass? And so we went and looked. And there it is. So this is my former student, Sam Whitebook, now a grad student at Caltech, showing that when we get radial velocities of the brown dwarf, they don't match the radial velocity of the star and they change in time. It's indicative of a massive companion. Contemporaneously to this, Jerry Schwann at Caltech put together a gorgeous data set. So these came out together, but his data looked better than mine did. This is with the gravity instrument, an interferometer on the Very Large Telescope, and he can actually resolve the orbit of these two brown dwarfs even over a period of hours. This is just astonishing. And so if you put all that together, is this still a weirdo? No, it makes perfect sense.
What's the period of that, the small binary then?
I believe it's a few weeks. I didn't put in the that period, but I think it's a few weeks. And so now this mystery is solved. The brown dwarf wasn't overly massive, it just had a friend. And finally, if we go back to HR 8799, that 4-planet system that we got so excited about early on in the field, this is a movie made by Jason Wong, then this star is also accelerating, so we can also get a dynamical mass for this system. It's basically just sensitive to the innermost planet because that's responsible for the largest share of the accelerations. But assuming you don't let the masses of the other planets go too crazy, you get a 20% first principles mass on HR 8799e. Just recently, we've extended this to be able to predict which new objects we will find. So in the same way that Neptune was discovered from perturbations in the orbit of Uranus, now we can look for tugs and motions in the space motions of stars to predict where we can look to find companions to those stars. If we have radial velocities also, we can even predict where to look. So here's an example where my student Yiting looked at this star with high contrast imaging, and we could predict even before we started that there should be a companion somewhere in those contours. And indeed, there it is. So this is a brown dwarf, not a planet. It's actually closer to a stellar mass. But we can predict its location before we even image it. This has most recently been applied to JWST to image old and cold planets that I don't know that we thought we'd be able to image until just recently when we started to pull it off. This is Epsilon Indi b, which I believe is the coldest exoplanet ever imaged. It's less than 300 Kelvin, maybe the oldest imaged exoplanet. And there it is. It's that bright point in the upper left. The star is the residuals from subtracting the starlight. And we don't just have a point of light, we have a mass and an eccentricity. So this planet is about 6 Jupiters with maybe non-zero eccentricity, but we'll see. And astrometry is a crucial ingredient to pin this down. Just recently, another example is AF Lep b, where this is a star, a young star without radial velocities, because young stars are hard to do with radial velocities. I'm sorry, this isn't AF Lep b, I'm sorry. This is 14 Hercules c, which is another one of these very old planets measured with JWST, where we had radial velocities And we could predict, again, where to look. We predicted below and to the right of the star, a little bit west of the star. And you see that point there. It doesn't show up in the shorter wavelengths. It does show up in the longer wavelengths where the planet is a little bit brighter. Here's maybe the most impactful one of these things, AF Lep B, where this star is young. And so the planet formed relatively recently. And yet we have this relatively precise mass measurement. So now you can start to ask questions like, when did this thing form? How long has it been cooling under various assumptions over over the physics of cooling? I don't have meaningful constraints on that now, but the cooling time is consistent with the age, and that age is getting young enough that we can kind of see how we might be able to apply meaningful constraints on the initial formation and evolution of planets.
Mass line with respect to your sort of mass gap, planets and brown dwarfs. Is it
It's solidly in
securely on the
the,
brown dwarf side?
it's solidly in the, so it's solidly in the planet section there.
Yeah.
Yeah, and this star is a little bit more massive than the sun. So if I put it at a mass ratio, then it'll be solidly in that kind of region. And this is something we can continue to do, so you can go look up radial velocity companions that have astrometry and predict where you might see something new. So if you want to write a JWST proposal, I think there are going to be some people who are going to propose for this one. I don't know if that one's taken, I'm not proposing for it, but go and you can see what you might want to find. And in the future, I know this is something Peter Melchior has thought about. If you add just a little bit more information off into the future, maybe you can do the same kind of trick we did with Hipparcos, where Hipparcos anchored Gaia into the past. Maybe something else can anchor Gaia into the future, and that something just might be the Roman Space Telescope. And so that's the idea developed here, that if you anchor Gaia into the future with just one more position, in the same way that Hipparcos' real value was anchoring Gaia with one more position into the past, that one position into the future can open up a new discovery space for a long period low mass companions that we might be able to actually reach. So I'll stop there, and I think the future is very bright.
Thank you very much, Tim. We have a little bit of time for some questions since we started a bit late, so the floor is open to raise your hand.
I was a little unclear on what happens when you have multiple planets. My understanding of, as you were describing the dynamics, was you're sort of doing the two-body problem. But if there are multiple planets at least close in, does the problem get yet more complicated to?
So the standard approach to this is to fit a linear combination of Keplerian orbits, neglecting the interactions between the true two-body process. Right. And so we do this, and it's necessary in some cases. For example, in HRH 799, we had to do this. For beta fit, we had to do this. There are a number of other examples where we do have to do this. And yes, that's it.
And like check stability.
If we're doing those fits, then the hope and assumption is that you're only going to do it if the fit is well enough constrained that stability is not a concern. If your fit is sufficiently poorly constrained that you would have to do some rejection for stability concerns later, then I don't think this is the right tool.
Could you comment on any other applications of this Gaia anchored to Hipparcos, like trying to search for other stars orbiting tensor mass black holes in the galaxy?
Oh, absolutely.
Binary stellar applications, etc. Has stuff been done with that?
So here, all this stuff in the top right is binary stars. So there's been a lot of binary stars and white dwarfs that I didn't highlight here. Yes. Those are easy because the perturbations are big. For black holes, we've looked, I know Kareem has thought about that quite a bit. We haven't found anything screaming like it is a black hole, but we haven't looked that closely.
Scott?
You described how you can use the Hipparcos Gaia proper motions to get not just M sin I, but M. So you also get sin I, and are they isotropically distributed?
I did not include the figure here, but for this paper, we can actually do that check. And the answer is essentially yes. I was extremely happy at how isotropic the result was. So I'll show you later, but it was pretty good.
Would your astrometric method work for planets around the central binary, like the one which was on archive this morning?
That is very difficult because it requires the astrometric measurements of that central binary to be clean. And if you have a binary, that's very difficult for something like Gaia to handle because it's not going to be so clean with the peaks and the astrometric positions. So I don't know that I would be able to trust the results very far for that application.
So you wouldn't be
which is
able to
hard.
predict the location of the planet a priori?
Well, if the astrometric data are good enough, then yes, you would be able to. So I'm just questioning whether the astrometric data for a binary are going to be reliable enough for you to do that, or whether it's just going to be noisy and messy because you're struggling to fit a model of a single point source to what is in reality more than one. It's not going to do that deblending for you. If you went and you did all the post-processing yourself, you'd probably get that back, but that would be an awful lot of work.
Are you getting anything interesting out of any spectra that you have? Do you have any spectra so far for the planet, for the planetary regime with any, I mean, you showed the low resolution spectra from Keras, I guess, and then anything with James Webb, any interesting information on the spectral features, model atmospheres, or anything like that?
So that is not my work. The JWST results are starting to get really high quality spectra of some of these planets and blind dwarfs. They have the usual suspects for molecules. I don't have any really surprising results to convey at the moment. There's one other system that completely orthogonal to this, but a pulsar planet, where the planet is a hot Jupiter. This was recently posted by Michael Shang. I did the data reduction for this one. And that pulsar planet has a mass of about 2 Jupiters. It's orbiting a millisecond pulsar. It's presumably the remnant of a stellar core. And its atmosphere shows molecular carbon, C2 and C3. And maybe hints of CH bonds, basically nothing else, no oxygen. That's weird. So if you want weird spectra, that's the weird spectra I have.
Excellent. So perhaps on that puzzling note, some across them all over, we will embark now for a call lunch, which will be in the Dwarf room per usual. Sorry for those online who might have been in the other room. Hopefully you can grab Tim at some other point to ask your own questions. Let's thank Tim once again for a really fascinating talk.